This is the screencast for section 5.6, examples 3 and 4. Both examples 3 and 4 deal with finding the area of a non-right triangle, but they give us two alternative formulas than what you're used to. You're used to 1/2 base times height. Well, what if you don't know the height? There is a way to find those. Depending on what kind of information you're given, you'll either use the area formula you see here, or Heron's formula, and we'll go on that. We'll show you that in example 4, and by we I mean me. Example 3, finding the area of a regular polygon. So we're asked to find the area of this octagon that is inscribed inside a circle of radius 9 inches. Well, this circle, the octagon is inscribed with radius 9 inches, meaning from the center of this octagon to each of its corner is 9 inches. So I know these sides. I also can figure out what one of the angles is in a single triangle within this octagon by taking the 360 degrees around this octagon and dividing by the 8 triangles that would be made by connecting the center to each of its corners. 360 divided by 8 is 45 degrees. So now I know a side, an angle, and a side, which means I'm going to use the formula you see up here. Now, similar to law of cosines, this formula has a pattern, so depending on what angle you're solving for, you use the other two sides within that formula. We're going to be solving for this angle, so we're going to use the other two sides, side, angle, side. So the area of the triangle, that's going to be of one triangle, is 1/2 times side times the sine of the angle, not cosine. So in my calculator I get that that's about 28.64, but I'm going to keep that exact answer in my calculator. So that's just one triangle area. I have to multiply by 8 to get the whole octagon. So the area of the octagon is about 28.64 times 8, which is 229.10 square units, which would be square inches. Then now try problem example 31. Same exact situation, except now the circle that the hexagon is inscribed in has a radius of 12 inches. So I still have side, angle, side that I'm trying to use to calculate the area of one triangle, then find the area of the hexagon. So I'm going to take the 360 degrees and I'm going to divide by the 6 triangles within the hexagon by connecting its center to each of the corners. And I get that each of those interior angles is going to be 60 degrees. So the area of one triangle is 1/2 times the side times the side times the sine of 60, which is about 62.35 square inches. But now the area of the hexagon is going to be 6 times that number I've saved in my calculator, 62.35 with a messy decimal, and that is going to be about 374.12 square inches. Now what if we aren't given a side, angle, side? What if we're only given all 3 sides? Well, technically you could use the law of cosines to find an angle and then use the formula we saw in example 3, but there is another formula. It's called Heron's formula. It's a 2-step process. Heron's formula revolves around this value they call S. S is the sum of all the sides divided by 2. So it is not the average, but it is the sum of all the sides divided by 2. So in example 4, S is going to be 13 plus 15 plus 18 divided by 2, 23. So now the area of this triangle is the square root of, put a 23 out in front, that is 23, the difference of 23 in each of the sides, that product. And then my calculator says that that is about 95.92 square units. The now try problem, number 21. Again, I have a side, side, side situation. The S value here is 4 plus 5 plus 8, all divided by 2, which my calculator tells me is 8.5. Which tells me then that the area of this triangle is going to be the square root of, going to put my S value out in front, 8.5, and then take the product of the difference of the S value and each of the sides. So 8.5 minus 4 times 8.5 minus 5 times 8.5 minus 8. And my calculator tells me that that's about 8.18 square units.